welcome to the lecture of the quantum mechanics. In this lecture, we will talk about the solution for the problem 2.16, which state that verify that the matrix cos theta, sin theta, minus sin theta, and cos theta. These are the entities is unitary. First, we will need to verify that this matrix is unitary or not. Then, and part B, we have to find its eigenvalues and the corresponding normalized eigenvector for this matrix. This is very famous matrices. We need it for the transformation and in many cases are deflection cases, how to rotate a particular axis around others. So therefore it is necessary to find its eigenvalues and the corresponding normalized eigenvectors. First, we find the eigenvalues of R, which is given matrix, by finding its secular equation, which is determinant of R minus lambda I is equal to 0. So R is the given matrices, minus lambda is the eigenvalues, and I is the identity matrix. As the previous we are following the context method in which we have evaluated all the matrices by formation of secular equation, then finding its eigenvalues. So R minus lambda and identity, this will lead to cos lambda theta minus lambda minus sin theta cos theta minus lambda, as the usual method of diagonalization of any matrices. Then determinant of R minus lambda I should be equal to 0. If we put this determinant equal to 0, this will lead to cos theta minus lambda square plus sin square theta. First, by evaluating this whole square and this sin square theta, this will lead to cos square theta minus 2 lambda cos theta plus lambda square plus sin square theta. Rearranging, we will have this lambda square minus 2 lambda cos theta plus cos square theta plus this. You know that this is equal to identity, so lambda square minus 2 lambda cos theta plus 1 will be equal to 0. This is the quadratic equation, and we can find its by the difference value of the variables roots. So if we use the quadratic formula, it will lead to lambda 1 2 is equal to minus b plus minus b square minus 4ac over 2a. That is the famous quadratic formula. This will give the roots of this equation, cos theta plus cos square theta minus 1. If we use some trigonometric identity, and we can put the value of this one as in the form of cos square theta plus sin square theta. If you are quite tricky or faster in solving mathematics, so we will have lambda 1 2 will be equal to cos theta plus minus iota sin theta. Now, if we recall the Euler formula for the cos and sin function, we know that cos theta is equal to exponential iota theta plus exponential minus iota theta over 2, and sin theta is equal to exponential minus iota theta, exponential iota theta minus exponential minus iota theta. And then if I center it, so lambda 1 will be equal to cos theta plus iota sin theta. Value of cos theta, you know that this, and value of iota sin theta is this. So we will put its value, and it will give us exponential iota theta. Similarly, we can find the value of lambda 2, which is cos theta minus iota sin theta. So the value of cos theta is this, and the value of iota sin theta is this. So this will give the value of lambda 2, which is exponential minus iota theta. Then now let's find the eigenvector and the corresponding to each eigenvalues. We will label each eigenvector by phi1 2, and phi1 will be equal to a and b, and similarly phi2 will be equal to c and d. So we will find the eigenvalues for lambda 1, eigenvector for lambda 1, and we will have here phi1 is equal to denoted by a over b. This will be we will find the value of a and b, and phi 2 is equal to c over d, we will find the value of c and d. First we find the eigenstate for lambda 1 is equal to exponential iota theta. So if we write r phi 1 should be equal to lambda 1 phi 1, r is the general methods and phi 1 is the eigenvector we are going to be find a and b, which value is a and b is equal to lambda 1. Lambda 1 is exponential iota theta and phi 1 is equal to a on b. Carrying out the multiplication on the left side, we have, if we multiply this matrix by this, similar this matrix, this will give us equation, and similarly on the right side. So if we multiply these two equations, this will yield this one, a cos theta plus b sin theta minus sin theta plus b cos theta, and on the right side we have this result. This matrix relationship give us two equations to solve along with two unknown a and b. A cos theta plus b sin theta is equal to this, and similarly minus a sin theta plus b cos theta is equal to this. Solving for b in term of a in the second equation, we obtain, if we solve the second equation, it will yield this equation, and recalling exponential iota theta is equal to cos theta plus iota sin theta, and plug in this, so it will give us b into cos theta minus this. So which from our previous result is equal to minus sin theta. So in term of a b is given by b is equal to a over minus iota, which can be written like a iota. So this allows us to write the eigenvector entirely in term of a. Phi 1 is equal to a over b, a is equal to a and b is equal to iota a. Okay, so b will be equal to iota a. So we have find out the value of a and b, because value of a is a and value of b is equal to iota a. Further, for the second eigenvalues, we form the matrix U from these eigenvectors. The first column of U is the first eigenvector, and the second column of U is the second eigenvector. So U will be equal to phi 1 and phi 2. So the first is phi 1 and the second is phi 2. If I go back, phi 1 over phi 2. So for the first, if we want to find phi 1 and phi 2, so its value will be 1 over under root 2 and 1 iota or 1 over under root 2. So you will surprise that from where 1 over under root 2 has come, and this is nothing but the normalization. If we normalize this matrices and divide it by normalization constant, so it will give phi 1. You know that the value of normalization constant will be first component square mean a square plus second component ka square, that will be iota a ka square. Okay, iota a ka square only. So we will write a square plus iota square a square and divide by this magnitude. So this will give the unit vector, which is phi 1. And similarly for phi 2, will be left with 1 over under 2, 1 iota over 2, and this. We can find the value of phi 2 as well as we have proceed for the value of phi 1, because for phi 1 we have chosen the value lambda 1, and for phi 2 will be definitely select the value for lambda 2, which is exponential minus iota theta. This will give also the value of a and c, value of c and b. So we can form its equation u is equal to phi 1 and phi 2. For the first normalized eigenvector is this, and for the second normalized eigenvector is this. Similarly, for phi 2 vector, we can find its normalized eigenvectors. If we write this phi 2 in term of the normalized eigenvector, it will be 1 over under 2 and minus iota over under 2. So we can take out 1 over under 2 common, and this will be U matrices, because for unitary this is the U matrices. So we take it transpose. Definitely we will have to change it 0 into columns. So this will give U transpose equal to this. As definition of unitary, U and U transpose should be equal to identity matrices. We have U and we have U transpose. If we multiply these two equations, this should equal to, this should give us to identity matrix as you are looking. So this result is identity matrix. Finally, we apply the transformation to diagonalize the matrix. If we apply a transformation matrix upon this to diagonalize, because we are actually going to find the diagonal matrix. So up to so far, we have obtained the two solutions which were asked. The first, we have proved that our unity transformation, U and U transformation, unity matrices, U matrix, our U matrices is unitary. And the second, we have found the eigenvectors for the given matrices, which is phi 1 A and B and phi 2 C and D. This is the diagonal eigenvectors phi 1 and phi 2. These are the two eigenvectors. This is the first phi 1 eigenvector and this is the second eigenvectors. Okay, you can find further solve it for the diagonalization. Finally, we apply the transformation to diagonalize the matrix. You know that from the basics of elementary algebra, we can find the diagonal matrix U transpose R and U. If we multiply this, we can find the diagonal matrix. So diagonal entry will be non-zero and all other entry will be zero. U dagger, this is U daggers. We will put the value of U dagger here, and similarly we are given the R is the original matrix and U. So if we multiply this two, so these should first we will multiply these two. This will give this matrix, and then we will multiply these two matrices. This will yield the diagonal matrix. You are looking that these two identities and diagonal entries are non-zero and all the other entries are equal to 0. And we see that the diagonal form of the matrix, the elements on the diagonal are the eigenvalues of R. So if we have a diagonal matrix, it means its eigenvalue will be just the diagonal element. This is the eigenvalues and this is also uh, the eigenvalues. So the basic purpose to find the diagonal matrix is to find the eigenvalues by shortcut methods. If we are succeeded in finding the diagonal matrix, it means we don't need to find its eigenvalues by any other method, just its primary diagonals entries are its eigenvalues. This is the first eigenvalues and this is the second eigenvalues. So I think I should stop here and we will proceed in the next lecture.